All right, we are live. Hello, everyone. I'm Maxwell Vogue, once again here from Learn at Home with the 3Doodler. Today we are going to be taking abstract concepts and making them a reality, which I am excited about because I like Newtonian physics. We'll be doing some math as well, so bear with me as we do that. But the objective of today's lessons, the first thing we'll go through, then the materials list of what you'll need to create your catapult. I'll show you how to doodle the catapult that we have. Then we're going to review what we learned, and then possible extensions, and then it's time for questions and other materials that we might have. So, realizing abstract concepts. So there are some ideas that are very hard or difficult to capture or explain by simply talking about them, and these are often better shown through demonstration, and we often find it easier to comprehend these. So we're going to do the catapult, or to demonstrate Newton's 3 laws. And if you're not familiar with Newton's 3 laws, the first law is an object in motion will remain in motion unless acted upon by an outside force, or an object in motion will remain in motion unless acted upon by an outside force. Second law is force equals mass times acceleration. And then the third law is, oh, I'm blanking. What is the third law? I'll go to the end of the slides, but they're all on the slides. That's embarrassing. Well, we'll hit the third law. Inertia, no, not inertia. I don't know. They're in the slides. So, pen prep. For starters, I'm going to be using the 3Doodler Create Plus today. This will be easier, the 3Doodler Create Plus, just because of the materials. Oops, sorry, my dog. Just because of the materials that we're going to be using. I'm going to be using the PLA. You could also do this with the ABS. Flexi would not be a good material for this one because it'll kind of crumple. And wood would also not be a good material for this because you'll break it if you bend it back. I will be looking at comments as we go along. Please make it fast and start to sketch. All right, I will get to the sketching then. So I'm using our desktop catapult stencil for this project. You only need a couple strands of plastic because it's not a particularly big project. Let's get to the doodling so I can see there's some desire for the doodling. So I have two sides, one back and one front. This is pretty straightforward in that I simply going to doodle on. I've added masking tape. You could just as easily use a doodle pad. I'm using the fast setting. I'm going to go nice and slow because I want these to be strong. So I'm putting a lot of forces and strains as we go along here onto the catapult itself. Once back over, and then I'm going to complete my triangle. Once again, we want these to be quite strong for this piece. And like I said, I am using PLA. You could use ABS for this. You are going to get different results, especially like the spring force or the K constant for the catapult will be different as a result of different materials. So that's an interesting kind of extension that can be done. This is the back of the catapult that I'm now just doing. This piece can be a little less thick, although you want to make one top piece thicker than the other. And I'm going to make the inside pieces. Like so. Alright, and then the launcher arm. You want to fill in that middle area there. we're gonna want to make a ridge for that as well. Let me just fill in this area. I mean, you could also do a net. It doesn't have to be a solid fill. It just has to be closed up enough so that whatever you're using as a projectile won't break through. And go across as well, just to make sure it's nice and strong. And then back over there, nice and thick. And once again, I want these sides to be thick. Ah, I know the strand plastic. I did most of this with just one strand, so I think we'll be able to do this with just 2 strands of plastic. All right. Back up again. Do my cross sections. Again with cross sections. And I'm not pushing down very hard, but I am pushing down on the paper to get it to stick. I'm going to do a little bit of a ridge, like so. So we need a basket to keep the object that we're catapulting in the catapult. The ABS plastic. But remember, all this stuff is hot. But it hardens very quickly. And I need one more triangle. And then I can join all these pieces together. You do want to make it as flat as possible on one side, whichever side you're going to make the bottom. Like so. All right. So now this is all filled. We can just round it off. You can see that it's quite springy. And same with this piece. And that's catapult construction time. So we're going to want to join the edge pieces here. Now, before you join it, if you really wanted to get into the physics of it, we could measure the weight of the arm itself, which is 2 grams. So that's something you might want to do, depending on how much of the physics you want to get into. Now I'm going to hold the 2 pieces, and I'm just going to put a dot of material to join them. Hold on, I'm going to do it flat. Dot there, and dot there, and then I can bend it, make a nice flat angle. Now I'm going to join it. I'm welding those pieces together. And you do want to kind of get in between those 2 pieces and make sure there's no gap. Make it nice and strong. And wait 2-3 seconds for it to harden. Do the other side as well. So I'll just do 2 dots. Now with the PLA, I have those 6 seconds before that material hardens, whereas the ABS you have only 3 seconds, so you have to be a bit faster when you're welding those pieces together. All right. Oh, my triangle is slightly off. But that's it. I'll make it. It'll still work. And then I'm going to weld from the side. So. And then I need my back piece. So it's again 2 little dots. this on. So. And now I'm going to put 2 dots at the bottom. There. Oh, this dot came off. So, draw it again. And then one more dot there. And then I'm going to join on the edge. Strengthen it up. And that'll give it a lot more rigidity. So. And then once again, join on the edge like so. And now I have, well, hold on. So I'm slightly off on my center of mass. So I'm just going to add a layer. Now I have a catapult that I can launch anything with. Now that works great, but what I'm actually going to do, I'm going to add a little extra pieces on here. I'm going to add just a little bit of a spoke right here on both sides. And you're going to see in just a second why I'm doing this. Like so. And the reason I'm going to do that is because we're going to measure the angle of this catapult. This is a catapult that I made earlier, somewhere. I think this one's like standing a little bit better. Gives you an idea. Look at the slides. So we saw me making it. Let's check if there's any. Someone's asking for some stuff. So demonstration. So we saw that we have objects. So now I'm going to get some projectiles. Now I'm using little ball and socket joints for my projectiles, but you could use anything. So let's go to that. So I can put my projectile in there. I can pull back, and I'm fired. And let's use the one that we just made. Projectile. Oh, I need to make that basket bigger. You can actually even see that that has a different force than this one. This one's a bit thicker, so it takes more force to pull it back. This is the one I did all of the fun math with. Let's go to slides. So Newton's first law is that is about inertia, and we're demonstrating with the catapult by making the object fly forward. As the catapult is bent back and released, you have a velocity on the projectile, but there's nothing stopping the projectile from moving forward, whereas the bar or the system itself of the catapult is stopping the arm from moving any more forward, so projectile goes flying. So an object in motion will remain in motion unless acted upon by an outside force. For Newton's second law, force equals mass times acceleration, the mass of the catapult projectile is accelerated across and actually falls back down to Earth using under gravity, which is negative 9.8 meters per second per second. So that's a great demonstration of that. And then Newton's third law, which of course I'd forgotten, is that for every action there's an opposite and equal reaction. And what that means is that once the ball actually strikes down on the ground, it's going to bounce because the force that it's hitting the ground with is the force that the ground is pushing back up with against it. But how can we explore these a bit more and get into it? We can use a protractor. Now, if you don't have one, you can doodle one. I simply went online and searched for printable protractor, printed it as actual size. There are maybe a dozen or even more that are printable on the internet that you can just print out, and then I doodled on the back, making sure to press down and do a good job, and I have a pretty reasonable protractor to do that. We can also use some tape and some fun stuff to do this. So what I did is I measured out a bunch of different times with the ball. I covered my projectile actually with some tape, with some painter's tape, like so. And then I used a tape measure with some tape on it as well to be the landing spot for the projectile so that I could get an accurate distance each time, as well as each time I measured with the protractor what angle I was launching off from. Just kind of review some, oh, here, I'll show you what the actual launch looked like. So as you can see, I've taped down the catapult, and I launch it out, and bam, it'll stick. So I can get a more accurate reading from the catapult, at least as accurate as we can do. I will answer some of the other questions not related to the lesson at the end, as well as I have some fun and exciting news for it. Now, there are some basic formulas for velocity and projectile motions. So we can see that velocity is equal to the change in the distance, or delta s, over the change in time, delta t. Angular velocity, which is when an object is rotating on an arm or around in a circle, is the same, but it's theta, or the degrees or the radians that it's changing over time. Acceleration is the change in velocity over time, same with angular acceleration. And then displacement, the distance that the object traveled as a result of coming out of the catapult, is the velocity, the initial velocity, multiplied by the time, plus 1/2 at squared. There's lots of ways of proving this, but they all derive from some of the fundamentals. And then motion change over time can be demonstrated there. I am going to kind of quickly go through what we can actually do with this, because I think it's a little fascinating. So you'll forgive me, but velocity v, which is a vector, so it has speed and direction, is coming off of the catapult. So we'll just make like a micro catapult here. And getting launched out at a specific thing. Now, it has an x component and a y component. So that is x and that is y, velocity. And then we have an angle, theta. And the great thing is so that we can determine that velocity is actually the y velocity plus the the x velocity. Let's read that up. V sub x. And to determine that, we can go to some basic trigonometry, SOHCAHTOA, sine over hypotenuse. So the v component is sine of theta times velocity, the initial velocity, equals the v sub y. And the cosine of theta, v sub I, the initial velocity, is the velocity in the x component. Now, when we're doing a problem like this, where we're launching out, our initial launch position from the catapult, A, B, and then C. So, we know that, give me my angles here. that the y component, or the y final, is based off of the height of the catapult. And then we could calculate it for any time period to find the maximum. The y final is the y initial plus the velocity sub y times the time plus 1/2 acceleration, once again, of the y component, time squared. And the x position is the initial position of the projectile plus the velocity in the x component in time. And then it is once again 1/2 at squared, but since we don't have an acceleration once we leave the thing, it's actually 0. And what the interesting is, this is a quadratic equation. You know, we have the y sub 0, and then we have the v times t, 1/2 at squared, which means that we can actually solve this all for t, because we know that our final height is actually 0. So it's already even laid out that this is a. Sorry, that is A, that is B, and that is C. So we can do our quadratic formula, if anyone remembers. Quadratic formula, so the time for the whole system, A through C, is going to equal, because time is going to be very difficult for us to calculate with a stopwatch. So it's easier to just do it in this manner. And if we remember the quadratic formula, the opposite of B plus or minus the square root of b squared minus 4ac all over 2a. And then we can simply plug those values in to determine what our time value is. We know acceleration in the y component is gravity. So our equation actually looks like this. Now I measured this earlier, and it's 2 inches. For the y sub y component where you start with the v sub y t plus 1/2 g, or we do it 9.8 or 32 feet per second squared. I prefer to do it in meters a second squared, and then the time. So using all of that, we can then plug it into the quadratic formula to determine what the time value is. And then to determine the velocity, we're actually going to have to do some initial experimentation by trying this out. So I did this. And I made a nice little Google spreadsheet here. As you can see, I measured the angles that we launched from in the end angle section, and then the distance that it launched using that method we described before. If you're doing good science, you should eliminate your top value and your bottom value, which is why those are in red, so those weren't calculated. And then the time is calculated from the formula that we just supplied, but the initial velocity is determined from solving for those two formulations, because velocity equals x squared, x sub v sub x squared plus v sub y. And we can determine all that. We can also use the mass to determine different ways of doing it, and the radians to determine the angular velocity or the angular acceleration of the whole system. So there's actually quite a lot that we can obtain from just the simple height of the starting point, which I have. Let's go to that real quick. From the height of the starting point, and then the theta, or the amount of angle that you're changing, as well as the launch angle. So by taking those basic pieces of information, you can solve a whole big range of stuff and demonstrate a large chunk of Newtonian physics. So don't stop there. You can obviously go quite extensive as to what we can do. As I was describing, you could literally determine everything about Newtonian physics by this one simple problem, and then extrapolate out all the equations by trying to solve it. Definitely trying to do different experimentations. You can use different materials to make the projectile, which will change the K constant, or the spring force, which you'll see from it. But this is a great way that you can take a project and go even further. I will answer some questions first before describing what we're going to have going on. So we have like a wheel. The trick for keeping your corners square when you're using the pen is, that's an excellent question, is that I'm on the surface that you're doodling on, and keep it perpendicular, or as 90 degrees to the paper as possible. It will also help to do it because the material is going to be sticking to that surface as a result. What other questions that we had? Please say, I don't know if I'm going to say that. I don't know what someone wants me to say something and I don't understand it, so to be on the safe side, I'm sorry. But I'm just not going to say it, Megan. Also last week, yes, I did mention you can smooth surfaces by baking things. I even showed you the thing that I'm making for lenses. These were all baked in an oven at around 220 degrees Celsius, so 425, 450 degrees Fahrenheit will work. It will kind of puddle out, so you do want to bake things flat or bake them over or on top of objects. So I used a spoon, for example, and I baked it in the spoon to create that and then popped it out. I used a little vegetable oil too to make sure that it would do a smooth, even heating surface. Any other questions? Yeah, I'm a graphic designer. Yeah. Some of this math is quite fun for me, so that's why I did that. But it's fair that some of you don't want to be seeing that. But there are quite a lot of great resources for determining all that math out there, so I would encourage you doing it. I'm not as good as some of the teachers that have been teaching it for quite some time, explaining just how much you can obtain from these basic facts of understanding the physics of a projectile. So I also want to mention next week we're doing a giveaway of a 3-doodler Create Plus as part of this series, and next week's lesson is actually going to be on atoms. We're going to be doodling atoms, so get ready for that, and then more instructions on how to actually win from watching next week's lesson will be there. Also, as a reminder that we have a Learn From Home pen set available now, which comes with an additional 250 strands of plastic as part of it for free, for the $79. And for the Learn From Home Start version, it's 200 strands of the Start plastic. So there's a lot going there. As always, please share with us on our social, @ or hashtag 3doodler. Love to see what people can do, making their own fun catapults. There's lots of different designs that you can do with catapults as well, so you can try different designs to see different effects as well as changing the material. Just tons you can do. See you next week, and have a great week, everyone. Stay safe.